At what angle above the horizontal should a projectile be fired so that its range, which is the x displacement magnitude, is 15 times the maximum height of its trajectory? Assume the projectile ends up at the same altitude it was fired from, ignore air drag. Okay, so what's going on here is we're firing some kind of projectile, and it's doing something like this. This right here, that would be its max height, which I'll represent with an H. And then from here to here, this is called the range, which I'm going to use a capital R to represent. That's the range. And this statement right here, it says the range is 15 times the maximum height. So I can turn that statement into an equation. The range is equal to 15 times the maximum height. Now, we've got formulas for the range and for the maximum height. The formula for the range is we take the initial speed squared times the sine of twice the initial angle, and we divide that by g. And then h is, again, the initial speed squared, but this time it's the sine squared of the initial angle, and it's over 2g. And I should mention, we're trying to find the initial angle. So everything's set up here. And this is the approach you want to use. You want to set it up like this. And then at this point, you should notice that some stuff cancels out. For example, I've got this vi squared here and this vi squared here. These cancel out. That's gone. That's gone. This g, that's gone. That's gone. And so what I'm left with is the sine of 2 theta initial. That's going to equal 15 sine squared of the initial angle and divided by 2. And of course I can reduce this down. I'll just go ahead and take it one more step here. Theta initial, this is really going to be 7.5 times sine squared of the initial angle. Okay, so now what? I can't cancel out the signs because it's the sine of something. That's the whole number. The sine itself is just a function. It's not a number. I need the sine of something. And I have two different things. I have the sine of twice the initial angle, and I have the sine of the angle, and then I'm squaring that. So what do we do? Well, what we do here is we remember our double angle formula. The double angle formula is that the sine of 2 theta is equal to 2 sine theta cosine theta. So I can come down here and rewrite this as 2 sine of the initial angle times the cosine of the initial angle equals 7.5 times sine squared of the initial angle. And what that means is now I can cancel out. This is the same as one of these. There's two of these being multiplied together. That's why it's squared, but they're the same. So I can cancel this out now. And then what I can do is I can go 2 divided by 7.5, and I can do the sine of theta initial divided by the cosine of theta initial, which is just equal to the tangent of theta initial. And so hopefully you can see what the last step is. The last step at this point is just going to be to take the arctangent to get the answer. to get theta initial. This problem is what I refer to as a challenge problem. But the neat thing about it, or at least what I think is neat, is that you are given one number, 15. Technically, you're given G as well, but we don't need to know G. We could be anywhere. We could be on Mars. You don't know what G is on Mars off the top of your head, and you don't need to because it cancels out, as does the initial velocity. This answer, as long as this condition holds, this is the correct answer for anywhere. As long as there's gravity, as long as you have this condition holding, which is going to be means there has to be gravity, then this is the answer. This would be the answer here on Earth. This would be the answer on Mars. It would be the answer anywhere. And just to get the answer, let me do that real quick. This works out to be 14.93 degrees.